this is R-2000, the better built house. We're here today at the airport. No, we're not at the airport. We're in the process of determining the air leakage characteristics of this particular house, and the fan helps us to identify weak spots in the shell of the building. We're going to find out more about that in a minute. We've already discussed the importance of air leakage control in energy-efficient housing. Today we're going to look at some of the factors that influence air leakage and why air leakage control is such a central theme in the better built house. In the last show, we looked at some of the design elements that go into reducing heat losses from a home. Here's a quick review. Last show, we discussed how heat flows through the surface areas of a house. We learned that heat loss from thermal bridging can be reduced by minimizing the amount of lumber that's used. And we discussed installation techniques that can improve the effectiveness of insulation. We learned that it's important to completely fill cavities with insulation and to restrict the flow of cold outdoor air blowing into the insulation by providing an exterior wind barrier. Okay, Oliver, now that we've got a better appreciation for reducing heat losses in a house, what's in store for today?
Well, we're going to continue to look at heat loss. It's a very important issue, but the way in which we're going to view it is from the point of view of controlled air leakage. Controlling air leakage is very important in a building, obviously from the point of view of energy consumption. It's very important for the comfort levels of the occupants of the house, and it's very important for the structural integrity of the building.
That sounds important.
It is. It's perhaps the single most important feature of the better built house. When one controls air flows, one also controls moisture flows. And that's why we're really concerned about it. Do you want to have a look?
Yeah, let's go.
What we have here is a cardboard model of a house, and we want to use that model to show how air leakage occurs in a building.
Well, it's a fancy model, Oliver, but obviously the air leaks out of the cracks and all the openings in the building.
That's partially correct, but in order for it to leak one way or another across the barrier of the wall, there has to be some pressure. A pressure difference can provide the push or pull you need to create airflow through an opening. A negative pressure will create suction, causing air to leak into the house, which is infiltration. And on the other hand, a positive pressure will force air out of the house. That's exfiltration.
So what kinds of things cause these pressure differences?
Well, there are several different things that do that. The first and most obvious one is wind. It could also be exhaust equipment in a building. And one that's less obvious is called stack effect. And what I want to show you with this model is that smoke put to the doors or openings on the box on the main floor actually enter the building, while smoke put at openings on the upper portion of the box exit the building.
The driving force is the light bulb you've got in the box.
That's correct. We've got infiltration taking place here. We've got exfiltration taking place here. And each of these things has a different effect on the house. The general pattern is for cold outdoor air to infiltrate at the lower floors of the house, and for warm household air to exfiltrate through the upper floors of the house.
So the name of the game in air leakage control is not only to just stop cold drafts from coming in the house, but to prevent the warm air from leaving as well.
Right on. You have to control both infiltration and exfiltration.
It's a pretty thorough approach you have. And so far we've learned that air leakage is influenced by wind, by exhaust equipment, and by the stack effect. Now, how do you tell exactly how leaky a given house is?
Let's go take another look at that fan. It's a really good tool.
This looks pretty sophisticated.
I can't hear you.
Well, turn it down. No, it looks pretty sophisticated, but basically this fan just exhausts air out of the house, right?
That's right, David. This fan exhausts 5,000 cubic feet of air a minute out of the house, and that air is replenished by air that's coming in through the fabric of the walls, and that enables us to find out where the leaks are.
I know how to find leaks in a boat. How do you find leaks in a house?
With a smoke pencil.
Oh, show me.
Let's go down to the basement. We'll give it a try.
Okay, you got me down here. Where are the leaks?
Well, I'd like to show you where this beam seat comes into the exterior wall. You see the discontinuous vapor barrier. You can see that there's some leakage there.
Some?
But take a look at this. That's the plumbing stack, and it's really leaky.
That's a hurricane.
It's a hurricane.
I guess windows are leaky as well.
They do leak a great deal. If you take a look along the edge here, you'll see that this is a slider, and it does leak quite a bit. But the surprising thing is that it leaks even more around the outside of the window from the way in which it's been installed.
It's pretty effective. Are basements sort of the worst place for leaks?
They're bad, but there are also a number of things to see elsewhere in the building. I want to show you the interior partitions.
Okay.
What I want to show you here, David, is this interior partition wall. And you'll see that the plug here is leaking just as badly as other leaks that we've seen elsewhere in the building.
I would have expected that on an exterior wall. How does that leak on an interior wall?
Well, it's because of the way in which the electrician ran the electrical wires when he wired the house. The thing to remember is that above us is attic space. It's really outside the building. And whenever there are holes left through top plates in the wall, those are going to leak as badly as any other leaks in the building.
This is all pretty typical for conventional construction, I understand. It's obviously a problem, right?
No, it certainly is. It's a very serious problem. What I want to show you is a house that's truly well sealed.
Okay.
David, this house has just been tested for the R-2000 pressure test, and it's passed. That means that this building is actually 6 times tighter than the house we were just in, and I'd like you to see if you can find any holes.
Okay. I'm new at this. Do I wait for the fan to get way up to speed? Or?
Yeah, well, it's coming up right quick. There you go.
Well, the smoke seems to be just drifting up on its own, but not because there's any wind coming in.
Sure isn't. The reason for that is because we've very carefully seen this poly barrier put in throughout the entire building. Goes up the walls, across the ceiling, everywhere. The builder has very carefully detailed it, for example, around partition walls here, where you can see that the poly has been run right through, and the wall has actually been installed after the poly has been put in place in this particular situation. All the doors and windows have been wrapped. The electricals have been very carefully taken care of at each electrical box. The plumbing stack has been sealed. All the places where we previously saw difficulty, we now don't have any.
So this is the famous continuous air vapor barrier. The fact that it is continuous and that there's no air leakage is it's the root of lower fuel bills and good air quality and all of those things?
Well, it's the beginning of all of those things for sure, but perhaps most importantly within the context of a wall section, it prevents the movement of water vapor into the walls, and that's really the key issue.
I have to confess that's not my forte, and moisture problems within wall assemblies. Where are the problem areas?
Well, there are a number of them of which we have to be very careful, and I'd like to show them to you. Here are a few shots showing obvious problems. This is a frost boil formed around a plumbing vent in an attic. When that melts, you can just imagine what's going to go on down below. This picture shows excessive frosting on roof boards in an attic. And this one shows exterior sheathing, badly deteriorated because of excessive moisture. Last summer I went swimming. Last summer I might have drowned.
Well, Oliver, it's a good thing you build houses better than you sing. What's going on?
Boo!
That's a nice outfit. What's the point?
Thank you. See those bottles there?
Yeah.
Those bottles contain the amount of humidity generated by a family of 4 in a 24-hour period.
Wow, that's a lot of water. Just from showers?
There are lots of other sources as well, David. Washing dishes, laundry, cooking, and also from the house itself, from wet basements or new framing, concrete that's curing. Between the family and the house, you can actually generate as much as 22 gallons a day. And all of that is generated in the form of water vapor.
So how does that water vapor turn into a liquid?
Come on, I'll show you.
I'm going to raid your fridge.
We've seen a lot of sources of humidity. When that humidity becomes a problem for us is when it condenses on surfaces. And that occurs whenever the air that's carrying it is chilled. For example, on this bottle where it's starting to condense now. Now, the reason that that takes place, if you would imagine this sponge as being the air, the ability of the sponge to carry water is reduced as the air gets colder and you drop that water out on the cold surface. Mm-hmm. Examples?
Yeah, well, all around the house, I guess, when you're having your shower on the cold bathroom window.
Precisely. Also in kitchen windows very frequently and a number of other places.
Nice basic science lesson. What's it got to do with building houses?
Well, to stop condensation, we have to stop water vapor from getting into a location where it will cool. We need to keep the vapor out of the walls.
So this is where the plastic vapor barrier comes in then?
That's right. But you got to keep in mind that 100 times more water gets into a wall as a result of air leakage than gets into the wall as a result of diffusion. So you have to have not only a vapor barrier, you also have to have an air barrier.
Ah, that explains the term air-vapor barrier.
Exactly. You can install a barrier which is for the control of diffusion, or you can install a barrier which is for the control of air leakage, or you can install a barrier which is a combination of the two, as in the case of the poly that we've been seeing in a lot of these houses.
Now, whether you're using two separate barriers or the combination air-vapor barrier, you still have to control air leakage, right?
That's correct.
Where in the wall assembly does that barrier go?
Well, we have a rule to cover that, and it actually changes depending on where you are, on how cold it is outside. But the rule that we use is called the 1/3, 2/3 rule, which is good for pretty much all of North America except the very far north. And it indicates that you can place the vapor barrier as much as 1/3 of the R value of the wall inside the wall itself, as long as 2/3 of that R value is on the exterior, so that the vapor barrier will always be warm, ensuring that we don't get condensation on it.
Now, I know that R-2000 homes are unique because of the control of air leakage.
They sure are.
How does this all affect that?
Well, one of the things that we have to be concerned about is any humidity that does, in fact, get past that barrier. And I'd like to show you what we do about that.
So, you want to prevent moisture from being trapped on the inside of this wall assembly.
The general rule is that the outside shell of the house should be looser than the inside. If the interior air and vapor barrier is effective, there should be no problem with the use of any vapor-resistant sheathings. But the key is that the inside be tight. Now, some real problems arise where the exterior part of the wall is tighter and water vapor gets trapped in the wall cavity.
That makes eminent sense. Now, what do you do about that?
Well, I brought you out here to see this paper. Now, this paper is not here just so that the manufacturer of this material can print his name on it. The purpose of this stuff is to act as a wind barrier, which is why it's been very carefully taped at holes and joints at corners and so forth. But it does breathe. It permits water vapor to exit from the wall cavity, so if any gets in there, it can breathe to the outside. This material, the paper, is called Tyvek. And in this particular case, the Tyvek has been bonded to an insulation material, an exterior sheathing called glassclad.
So does it limit you then to having to use something like this product on the outside for sheathing?
No, because you can also buy it as a paper. In this case, you just have the Tyvek in a roll. It comes 9 feet long, and you can just roll it around the house.
This is one of the clues why energy-efficient housing is cheerfully colored and ordinary buildings are black. Why don't you see these kind of materials on regular houses?
Well, you do, and you're seeing more and more of them. But this material is 4 times more expensive than your regular building papers, so frequently builders think about it before they buy.
So here comes that issue where you have to kind of trade things off for their cost and their effectiveness. Is that right?
Always.
Well, gee, we've covered air and vapor barriers, and also air-vapor barriers, and the 1/3, 2/3 rule, which I have a feeling is going to keep coming back on me. Am I right?
It's going to come back a lot. The argument here is that if you understand the building science issues behind the selection of the materials and their use, you can buy the right thing and do the job properly in the field.
Good speech. Now, you know, it's kind of great being out here with all this mud and stuff. We're going to get to the construction sites now?
Almost. But before we get to the construction sites, I want to show you where you select these materials, because that's something that's going to come up a lot. I want you to meet me at a building supply place.
Okay, so join us in the next program on R-2000, the Better Built House.